welcome to this lecture of this course Computed Power System Analysis. So, we have been discussing FDLF. So, let us continue. So, we have been discussing, we were talking about J3 and J3 is del Q by del theta. So, let us look at the expression of del Qi. So, before that let us look at the expression of Qi. Qi is Vi, Vj, Yij sin theta I minus theta j minus alpha ij, j is equal to 1 to n, and we as usual we take the ith term. So, Vi square minus Bii Vi square plus j is equal to 1 to n not equal to I Vi Vj Yij sin theta I minus theta j minus alpha ij. Now, we look at the expression del Qi by del theta j, where j is not equal to I. So, that should be, this part would be gone and there would be only one term. So, it would be minus Vi Vj Yij cosine theta I minus theta j minus alpha ij. So, it would be minus Vi Vj, and we have already seen that this part can be written as Gij cos theta I minus theta j plus Bij sin theta I minus theta j. And we have already seen in the last lecture that this part is 0 and this part is 0. So, we have seen that this is equal to 0 and this is almost equal to 0. So, then therefore, this is also almost equal to 0. So, then therefore, we have this result that delta Qi by delta theta j, j not equal to I is equal to 0, approximately equal to 0. We should not say it is exactly equal to 0, but under these assumptions these are equal to 0. So, this is 0. Now, what we have? We have del Qi del theta j, where j is equal to I. So, then therefore, all these terms will come into picture except this, because this does not have any theta I. So, this would go and it would be j is equal to 1 not equal to I Vi Vj Yij cos theta I minus theta j minus alpha ij. Just now we have done this exercise and we have seen that this part after expansion becomes 0. So, this part after expansion becomes 0. So, then therefore, we have got this another interesting result that del Qi by del theta j subject to j is equal to I, that is when j is equal to I, this is also equal to 0, or in other words, because both this term as well as this term are 0. So, then therefore, we write this matrix is also a null matrix, and we have already seen in the last lecture that J2 is also null matrix. So, J2 is also a null matrix that we have already established in the last lecture. So, then therefore, what we have is now we have J1, then it is 0 null matrix, then it is another 0 null matrix J4. J4 we have not as yet looked at, but this is we are just delta theta delta V is equal to delta P delta Q. So, then therefore, if I simplify this or rather write down the equations individually, what we get J1 into delta theta is equal to delta P and J4 into delta V is equal to delta Q. So, now what happens you? So, from these two equations we can see that variation of theta is only dependent on variation of P and variation of V is only dependent on Q. Earlier, when this matrix was a full matrix, that is when J2 and J3 were not null matrix. So, then in that case variation of theta is actually dependent on both P and Q. Similarly, the variation of V is also dependent on both P and Q, but here in this case after this application of this simplifying assumptions, we find that this variation of theta is only dependent on P, it is not at all dependent on Q, and variation of V is only dependent on Q, it is not at all dependent on P, or in other words this theta and P and V and Q, they are decoupled from each other. So, theta is only dependent on P and V is only dependent on Q. So, then therefore, these equations are actually decoupled equations. So, that is why we call them as decoupled equations. And in normal power system terminology, we call this that it is theta and P coupling as well as V Q coupling. That is theta is only dependent on P and V is only dependent on Q. So, we call it theta P coupling and V Q coupling, that is exactly where it is. Variation of theta is only dependent on variation P and variation of V is only dependent on variation on Q. So, that is why it is called decoupled equation. So, our topic is fast decoupled load flow. So, we are trying to solve the load flow equation. So, we have seen that after the application of this simplifying assumptions, these load flow equations get decoupled from each other. So, that is why these are called decoupled load flow. Now, why it is fast? So, for that we have to now look into in little more detail into the expressions of J1 and J4 and apply these simplifying assumptions again. So, let us do that. So, we look at J1, J1 is del P by del theta, we know. So, it has got del Pi by del theta j, one is j is not equal to I, and del Pi by del theta j is equal to I. So, these two cases are only possible. This is a square matrix we already know, and we also know that I and j both vary from 2 to n. So, these are all known, we are just recollecting. So, Pi we again write down that it is Vi square Gii plus j is equal to 1 to n not equal to I V I V j y I j cos theta I minus theta j minus alpha I j. So, now we first do the simplified one. So, we first do del p I by del theta j, j not equal to I. So, what we will have, of course, this partial derivative of this term would be 0, and because j is not equal to I. So, then therefore, there will be only one theta j term and it would be V I V j y I j cosine minus sine theta I minus theta j minus alpha I j. We are doing the partial derivative with respect to theta j. So, cosine have got a partial derivative minus and we have got another minus. So, minus minus plus. So, now we have to expand this V I V j y I j. This is sin a minus b. So, sin a cos b minus cos a sin b. So, it is V I V j y I j into g I j sin theta I minus theta j, and it is becoming V I V j, it is B I j cos theta I minus theta j. Now, here we again put the simplifying assumptions. So, what are those assumptions? Assumptions are again the same assumptions. So, we have already seen that this is almost equal to 0, this is also almost equal to 0, this is not 0 and this is almost equal to 1. So, then therefore, because this is very small, this is very small. So, the entire term gets vanished. So, then therefore, what we are left with is it is now almost equal to V I V j B I j. So, what assumptions we have taken here? So, we have taken the assumptions that theta I minus theta j is almost equal to 0. So, then therefore, cosine theta I minus theta j would be almost equal to 1. So, then therefore, we make it unity. First of all, this is neglected. So, this is gone. So, what is remaining is minus V I V j B I j cosine theta I minus theta j, and because theta I minus theta j is almost equal to 0. So, therefore, cosine theta I minus theta is almost equal to 1. So, then ultimately we have got del p I by del. So, this is equal to minus V I V j into B I j, right. So, we have got this. So, we have an expression. So, we write this expression delta p I by delta theta j is equal to minus V I V j B I j. Condition is that j is not equal to I. So, from here I can write down that 1 by V I delta P I by delta theta j is equal to minus V j B I j for the condition j is not equal to I. Now, here we invoke the assumption that all voltage magnitudes is equal to 1, but we only invoke the assumption only at the right hand side, but not at the left hand side. So, if we invoke this assumption at this right hand side, so we get for the condition j is not equal to I, Now, the question becomes that why are we only invoking the assumption at the right hand side, but not at the left hand side, because at the left hand side also we have got one voltage term V I. The answer is this, that when we invoke this assumption at the right hand side, this right hand side terms becomes constant, because you see this quantity Bij is entirely dependent on the line parameters, which is constant. So, then therefore, once we calculate this parameter Bij, it remains constant, we really do not have to calculate it at each and every iteration. So, to make the right hand side constant, we invoke this assumption at the right hand side. But if we apply this assumption at the left hand side also, it will actually increase the error in our calculation, because see, after all these bus voltage magnitudes are equal to 1, this is just an assumption. So, then when we are invoking this assumption at the right hand side, we are already incurring some amount of computational error just to make it constant. And if we again invoke the same assumption here, so then therefore, it will actually increase the computational error as compared to this ideal solution. So, then therefore, we do not invoke this assumption at the left hand side just to reduce this computational error, but we only invoke this assumption at the right hand side, such that this right hand side is constant. Now, because this is constant, it has got a very good implication, which we will see a little later. So, we this. Now, we look at the expression del pi by del theta I. We get from the expression of minus, it is minus j is equal to 1 to n not equal to I V I V j y I j sin theta I minus theta j minus alpha I j. So, what we do here is we do an intelligent thing V I V I y I. So, V I square y I sin theta I minus theta I minus alpha I. Because we have added this term, we must also subtract this term to maintain the sanctity of the expression. You may be wondering what is happening, but it will be very clear in a moment. Alpha I, and then this entire expression j is equal to 1 and not equal to I n V I V j y I j sin theta I minus theta j minus alpha I j. Now, if we look at these two terms together, here in this entire term j is not equal to I, and in this term j is equal to I. So, you see this j is equal to I, this j is equal to I, this j is equal to I, this j is equal to I. So, then therefore, if I take them together, so what I get, and this term is V I square into y I into sin minus alpha I, and sin minus alpha I is minus sin alpha I. So, then there it is minus V I square B I. So, then this term becomes, so del P I del theta I, it becomes minus B I V I square and then minus j is equal to 1 to n V I V j y I j sin theta I minus theta j minus alpha I j. So, this is it. Now, this term we get by combining this and this together. Now, we know that this is nothing but q I, this we already know. So, then therefore, we write it is minus p I v I square minus q I, and please remember, please recollect our last assumption that in magnitude q I is much less than b I into v I square. So, then therefore, it becomes minus b I v I square. So, then therefore, we have 1 by v I into del p I by del theta I is equal to minus v I b I. Invoking this assumption that v I all voltage magnitudes are equal to 1.0 only on the right hand side, as we have done just a little while ago, we get 1 by v I del p I by del theta I is equal to minus b I. So, this is the interesting result. So, now what happens? So, this is J 1. So, this is the expression of J 1. So, this is the first, and we write again the second one just for the clarity, and for the second one is 1 by v I del p I by del theta j is equal to minus b I j. This is for j is not equal to I. So, this is the second condition which we have just now developed. So, now what happens? So, we have got some constant quantity. Now, let us look at the last one, J 4. J 4 is del q R del V, and it has got two terms, del q I by del V I and del q I by del V j, where j is not equal to I. Now, we know that I and j all both varies from m plus 1 to n. So, q I is b I v I square, it is minus plus v I v j y I j sin theta I minus theta j minus alpha I j. So, del q I by del V j, where j is not equal to I, it will become, this part would be 0. So, it would be V I y I j sin theta I minus theta j minus alpha I j. We have already seen that this part is nothing but g I j into sin, etc., etc. So, it is g I j to sin theta minus theta j minus theta j. Invoking this assumption, we get so, then therefore, if I again invoke this assumption that V I is equal to 1.0, what I get is del q I by del V j is equal to minus b I j, j is not equal to I. So, this is the assumption. So, this is the equation, again this side is constant, and the last one it is 2 V I B I I plus G is equal to 1 not equal to I to n V j I I j sin we multiply everywhere by this. We are multiplying everything alpha I j. We minus V I square B I I and minus V I square B I I, then plus this minus alpha I j. So, then therefore, if I do add them together I get this. So, I get minus V I square B I plus j is equal to 1 to n V I V j Y I j sin theta I minus theta j minus alpha I j. This quantity is nothing but q. So, then therefore, it is minus V I square B I plus q I, this part is q I, and invoking this assumption that q I is as magnitude much less than this. So, we get this V I del q I by del V I is equal to minus V I square B I, or in other words del q I by del V I is equal to minus V I B I, or in other words del q I by del V I. Again invoking this assumption that V I is almost equal to 1.0. So, these are the expressions of J4. So, we have got these expressions of J1, J2, J3, J2 and J3 are already made 0. For J1 we have got these two expressions, and for J4 we have got, so we have got one expression is this and another expression is so this is for J4, and we again for J1 we write that 1 by V I del P I by del theta j is equal to minus B I j, j not equal to I, that is this one we are just recollecting them 1 by V I del P I by del minus B I j, j is not equal to I, and this is V I, and we have got 1 by V I del P I by del theta I is equal to minus B I. So, you have got this expression and I have got this expression. So, this is for J 1 and we already seen that J 2 is 0, that we have already seen, and J 3 is 0. So, we have derived this expressions of J 1 and J 4 and we have already seen that J 2 is a null matrix, J 3 is a null matrix, and J 1 and J 4 all these terms without the application of this assumptions become constant. So, now we will see that how this expressions are applied for our for the solution of our load flow equations and how the application of this really make the load flow solution process fast. So, this we will look into the next lecture. Thank you.